So this is the start of the third unit, Set Theory and Logic. A little bit of a different start to this unit. I've got a couple of, I'm going to call them logic puzzles for you to try. You'll notice that they are from old exams. So this is kind of strange because we don't really have a lesson on logic. It just requires you to do some analysis and thinking. So what I'd like you to do is try these few questions. So you can see there are several of them from old exams. Try them on your own. We will discuss them in class. Okay, so leave those. I've also got a vocabulary of sets worksheet here. If you want to, you can go to this website. This will fill it out for you. This is just for you to have sort of a diagram to match every definition. Okay, you don't need to do this, but if you think that this would help you, then feel free to do that. Okay, we're going to start this lesson right here with a bunch of definitions. And again, you don't need to know the definitions, but you need to know what they mean and how to use them. And it's funny, for the most part, most of these lessons are very simple. It's the notation that becomes confusing. Okay, the idea of sets is very simple. Okay, here's a set, all the whole numbers. Okay, very easy. We can just list them. Okay, an element is one of the objects in the set. So for example, 3 is an element of D. Again, these are not difficult concepts. Okay, but we're going to get into some other language that makes it a little bit more complex. So let's continue here. Universal set, the set of all the elements under consideration for a particular context, also called a sample space. So for example, the universal set of digits, so all the digits, this is the universal set right here. Those are all the digits that we make numbers out of. Okay. A subset is a set whose elements all belong to another set. For example, the set of odd digits. Okay, the set of odd digits is a subset of D. If you can notice, 1, 3, 5, 7, 9, they are all in that set. Okay, so that makes them a subset. In set notation, we use this right here. Odd digits is a subset of all the digits. Okay? A complement is all the elements of a universal set that do not belong to a subset. Okay, so for example, if the odd digits are 1, 3, 5, 7, O prime, this means that the complement of O is all of the numbers that aren't odd. In this case, that would be the even numbers. Okay, if you add O plus O prime, it should give you all of the values or digits in the main set. Okay, empty set. Empty set is denoted by putting an empty set inside the brackets like that. Okay. For example, an empty set would be the set of odd numbers divisible by 2. Well, you know that there are no odd numbers that are divisible by 2, so we would have an empty set there. Okay, disjoint means 2 or more sets having no elements in common. For example, the even numbers and odd numbers are disjoint because they have nothing in common. A finite set ends, it doesn't continue, whereas an infinite set continues, denoted with those little dots. Mutually exclusive, if 2 or more events that cannot occur at the same time, for example, the sun rising and the sun setting, those are mutually exclusive events. Okay, so let's take a look at some notation. So this is the part that's a little bit tricky. So sets are defined using brackets. So if we say the universal set 1, 2, and 3 is here. So we're using U to show this is the universal set. We use these set brackets to show all the numbers that are included. And then we define a set A that has the numbers 1 and 2 as elements. So this is a subset of U. Since all the elements in A are also elements of U, we can say A is a subset of U. Okay? The set A prime, in other words, the complement of A, would be written as A with a little prime symbol. And what's not in A? 3. 3 is the only element that's not in A. Okay, and then so to define the set B, which is a subset of U that contains the number 4. Well, we know that 4 is not in the set of U, so B is the empty set. Okay? All right, let's try a few questions. So, first one says, indicate the multiples of 5 and 10 from 1 to 500 using set notation. So first of all, let's list what is the universal set here. Okay, the universal set, maybe we'll write this. The universal set is what? It's all of the numbers from 1 all the way to 100. Okay, and now we've got some subsets. Okay, let's call M, sorry, not M, let's go F, just to make it simple. M is the multiples of 5. Okay, so which numbers are the multiples of 5? They are the numbers 5, 10, 15, ... all the way up to 500. And then let's call the multiples of 10 call it T, and it would be 10, 20, 30, ... all the way up to 500. Okay, now there's nothing very complicated about that. We've just drawn 3 sets. We've called the universal set the numbers 1 to 500, and then the sets F and T are subsets of U. All right, so let's start looking at some questions that you might be asked about this. Represent the sets and subsets in a Venn diagram. Well, have you seen a Venn diagram before? It's very basic. Here is the universal set. These are all of the numbers from 1 to 500. Okay? Then in this set, some of the numbers fit into F. Okay, those are all the multiples of 5. And then in the set of F is a subset T. Okay, because, for example, where would you put the number 10? Well, the number 10 would go here because it's in the set T, which is in the set F, which is in the set U. Okay, on the other hand, 5 would have to go here. And then let's say a number like 6 would go here because it doesn't fit into either of those sets. Okay? In fact, we could call this F prime out here. Right? These are all the numbers that are not F. Okay? So there is the Venn diagram. Pretty simple stuff. Let's try another question. So the triangular numbers. Triangular numbers are 1, 3, 6, 10. What would the next one be? Well, you would have to have one more row. And how many are there? I believe that's 15. Interesting patterns here. What are you going up by here? 2, and then 3, and then 4, and then 5. What would come next? You would add 6, right? So what's the pattern? What is the pattern to determine the triangular numbers? Well, you're just going to keep adding the next digit. So the first one is 1. And then you go 1 plus 2 is 3. And then you go 3, which is here, plus 3, okay, equals 6. And then you take 6 and add 4. So you can see we're going to add one more each time. All right, then we'll take 10. What would you add to 10? You would add 5. And then you would take 15 and you would add 6. And then you would take 21 and add 7, etc. So that's just a pattern. I guess you could call that using some logic. You know, there's not really any math there. That's just kind of figuring out the puzzle. Now let's look at the sets. Determine how many natural numbers from 1 to 100 are even and triangular. Okay, let's write some sets out here. What's the universal set? The universal set is 1, 2, 3, 4, all the way to 100. Then let's look at which are the triangular numbers. They are 1, 3, 6, 10, 15, ... Well, maybe this time we need to write them all because I don't really know what this pattern is. So we'd go 21, add 7, add 8, add 9, add 10, add 11, add 12, add 13, and then we're done. Okay, now here's another little bit of new notation. The number in the set T is 13. So in this case, N refers to the number of elements in T. Okay? Now, we're also supposed to figure out what are the even numbers. What are the even numbers? Okay, the even triangular numbers. Well, let's just look. So we've got 6, we've got 10, 28, 36, 66, 78. Okay, the number of even numbers is 6. Okay, let's now look at odd. Why am I doing this? Well, if you look here, it's asking us about odd, even, and triangular numbers. So we need to figure out these sets. What are the odd triangular numbers? 1, 3, 15, 21, 45, 55, 91. Okay, and the number of odd is 7, which makes sense. 6 plus 7 is 13. There are 6 even, 6 odd, or 7 odd. There are 13 in total. Okay. Now what are we supposed to find here? We're supposed to find the number of even and triangular. That's this part right here. Then the number of odd and triangular right here. And then we're supposed to find the ones that are not triangular. Okay, so this is not triangular. They're the non-triangular numbers. How are we going to do that? Are we going to write them all out? Well, there's a bit of a shortcut to this. I mean, we know that there are 2, 4, 5, 7. These are all the ones that are not listed. Okay? But there's an easier way to do that in this case, and that's to use some set notation. So the number of non-triangular numbers would be the universal set. Okay, take away the triangular number set. And it's really the number of the universal and the number of the triangular. So there's 100 elements in there, and there were 13 that were triangular. This means that there are 87 non-triangular numbers. Okay? Now, quick question here. You can look at this notation comment here. Let's go to see how many numbers are triangular. So if we don't go from 1 to 100, if we look at any numbers, how many are triangular? Well, don't forget that that list we had would go on forever. So there is an infinite number in that set. So no matter what number you think of as a triangular number, there's always going to be one bigger. Okay? Let's go to the next example. Alright. Now you're going to see again that the question itself is not that difficult. It's maybe figuring out what some of the notation is. So Alden and Connie rescue homeless animals and advertise in local newspapers to find homes for the animals. They are setting up a web page to help them advertise the animals that are available. They currently have dogs, cats, rabbits, blah, blah, blah. Design a way to organize the animals on the web page. Represent your organization using the Venn diagram. Well, first of all, let's have our first set being all animals. And then what are some subsets? Well, I guess we could say warm-blooded. Now, this doesn't mean that this is the only way you could do it. Alright? And then we could say cold-blooded. Maybe you come up with a different way. Okay? Maybe you say, instead of cold-blooded, maybe you say reptiles. Okay? That you could do that. You know, if you decide that would be your name. The problem with warm-blooded is you've got two kinds. You've got the mammals, like these are two subsets, and you've also got birds. Okay? So let's see if we can put this into a Venn diagram. So our set here is all animals. How many animals were there? We don't know. It doesn't tell us how many there are. Okay? But in the set of animals, we have two subsets. We could say they're warm-blooded and cold-blooded. If you decided to call them something else, that would have been fine. Inside the warm-blooded, we have two kinds. We have mammals and we have birds. Okay? So there's a simple Venn diagram. I mean, it's not the only one, but that's a possible Venn diagram. Okay. Then it says, name any disjoint sets. So disjoint means they can't overlap. Okay, so for example, the warm-blooded and cold-blooded, there's going to be no overlap there. They can't be both. The mammals and the birds, those are disjoint. Mammals and cold-blooded are disjointed. So are birds and cold-blooded. Disjointed. Nothing overlaps. Okay? Part C says, show which set are subsets of one another by using set notation. Okay, this will be a little bit different. What are some subsets here? Well, M is a subset of W. D is a subset of W. Okay? But also M is a subset of A, as D is a subset of A. Okay? We can also say W is a subset of A, and C is a subset of A. Okay, this is supposed to be like a sideways view. Sorry if that doesn't look very clear. Okay? And last question. Alden said that a set of fur-bearing animals could form one subset. Name another set of animals that is equal to this subset. Well, fur-bearing would be like mammals. So as I said, we could have had different names, but those are just the ones I chose. Okay? So let's do one more question here. Juliana recorded the possible sums that can occur when you roll two four-sided dice. So for example, if we roll a 1 and a 1, the sum would be 2. That's one example. Okay, if you roll a 4 and a 3, the sum would be 7. Okay, that's what this chart means. Okay, display the following sets in one Venn diagram. The rows that produce less than 5, let's call that L, and the rows that produce greater than 5, let's call that G. So here's our subset, our Venn diagram. This is the universal set. This is all of these outcomes. Okay? Inside there, we have a subset where these are numbers, these are combinations that are going to be less than 5. For example, 1 and 1, 1 and 2, 2 and 1, 1 and 3, 3 and 1, and 2 and 2. Those are all sets that will give us a sum that is less than 5. Okay? What about greater than 5? Well, what would give us greater than 5? Well, 4 and 4, 4 and 3, 3 and 4, 3 and 3. Any others? Greater than 5? Sure. There's 2 and 4, and 4 and 2. Okay? Now, there's a couple of combinations that don't fit there. They're not less than 5 or they're not greater than 5. They're actually equal to 5. These would not fit in either of those two subsets. Okay? So there is the Venn diagram. Record the number of elements of each set. What is the number of L? It's 6. What is the number of G? It's 6. What is the number of the universal set? Well, there are 16 outcomes. Okay. Last one, determine a formula for the number of ways that a sum less than or greater than 5 can occur. Verify your formula. Okay, so this is the number of ways. So how can you get n of L or G? So how could we get the number that is less or the number that is greater? Well, that's easy. We would add the number of less with the number of greater. That would give us the right total. 6 plus 6 equals 12. Okay, so there is the lesson. There's some thoughts here that you can look through. Okay, you should read it through. Should be clear because we've already done some of this stuff. Okay. Okay, in addition to doing the logic puzzles at the beginning, you can also finish this for homework.